So first of all, the spectroscopy, it is basically the measure the electromagnetic wave come from the sample. And talking about electromagnetic wave, there are all different kinds of waves. It depends on the frequency and the wavelength. The electromagnetic waves is made of packets of energies, which we call them photons. It sounds like a particle, but it's actually the energy. And as the electromagnetic wave, it has both wavelengths and frequency. These two are the very key features of certain waves. So this is the full spectrum of the electromagnetic wave. Start from very short wavelengths, gamma radiation, very high energy, and get into the X-rays, UV, UV visible, infrared, and then infrared is where the heat, normal heat, our body can sense the heat, come from the infrared radiation. Even longer wavelengths get into microwave and radio wave and so forth. So that's a full spectrum of the electromagnetic radiation. As the infrared, we focus on the wavelengths in the micrometer range. And so the spectroscopy, because the radiation or electromagnetic radiation being absorbed or being emitted depends on the energy level within the molecules. Energy level within the molecules. We can obtain information about the structure within the molecule. And such as the NMR, nuclear magnetic resonance spectroscopy. And that is, we measure the molecules absorb the radio waves. And that can tell us how many atoms, and even the same atom, their chemical environment different, can tell us. So the NMR in the next semester, you'll find is very, very powerful tool to identify the molecules. Infrared is much cheaper to operate because it measures the absorption of the infrared radiation, and it can tell us what functional groups. Oftentimes, it can tell the functional groups what is in the organic molecule. UV vis, this is the absorbance in the UV range and the visible light. This part of the radiation, it tells us how many pi bonds are linked together next to each other. And this we call them conjugated pi systems. It has very limited usage in chemistry. So the infrared IR or infrared spectroscopy, we basically measure how much sample absorbed in the infrared light. And so the way we do that is we put a sample onto a salt plate. The salt, such as sodium chloride, absorb almost no infrared. So it's basically infrared transparent. We use this plate as a background to support and measure sample. Sometimes we can directly measure sample, such as in our experiment, our lab. We directly measure sample infrared radiation. So the infrared radiation comes from the energy level within the molecule when the bond have these are basically two kinds of vibrations within the molecules. There is a simple stretching, and there's oscillating, the bending, bond bending. And these vibrations, each one using quantum mechanics, we can calculate the energy level. And those energy level difference, it corresponding to the infrared being absorbed, by example. And our chapter focuses on more on the stretching frequencies. The bond vibration energy level. So for example, the hydrogen, carbon-hydrogen bond, there's a larger gap in the different bond vibration energy levels. Larger gap, that means it absorbs higher frequency infrared radiation. And the carbon oxide bond being the oxygen being a heavier atom, the gap between the energy level is smaller. So the electromagnetic radiation being absorbed will be the longer wavelengths, longer wavelengths radiation, infrared. So you can see the difference. That shows us the frequency of the absorption. It can lead us to find out what kind of atoms in the molecule. And so that's it. So basic principle for the infrared spectroscopy is we measure, compare with the background, how much sample absorb at certain frequencies. We can measure the wavelengths or frequency where the absorption takes place. And also we can measure how strong or weak the infrared being absorbed. So both can tell us information. This kind of shows you example, the ethanol. Ethanol molecule, you have a CH bond, CC bond, and there's CO bond, and OH bond. Each bond, the vibration, they give us specific frequency and strength. So you can see the OH bond absorb fairly high frequency. And CH bond, because there are 5 CH bond in the molecule, it absorbs fairly strongly. And finally, there's a very strong carbon oxygen absorption. So all these can tell us information about the molecular structures. So like I said, this is the real example of how the infrared looks like. You have the Y, it is transmittance, or how much being absorbed. The higher transmittance means lower absorption. And typically we discuss about absorption. Absorption, which means the downward peak. The longer downward peak, it means stronger absorption. So you can see the X, it is a wave number. Wave number is the inverse of the wavelength. So the wave number is proportional to frequency. As we know, the electromagnetic radiation frequency will decide the energy for the photons. So basically the X, it is in another way, it is how much energy such bound vibration absorbs. These are the high numbers, means high frequency, higher energy infrared being absorbed. And these are the lower energy being absorbed. And so the frequency, the wave number, because electromagnetic wave travels at the same speed in the vacuum. It's almost 300,000 kilometers per second. And the speed equals frequency times the wavelength. So therefore, the higher frequency will give us a lower wavelength and so forth. This is we learned that in the general chemistry or intra-chemistry. The wave number, it is inverse wavelength, because wavelength in meters. So the wave number, the unit is inverse of the length. If you use centimeter, that is inverse centimeter. And so the infrared, how we use in the organic chemistry, it depends on what kind of bond. And each bond have a very specific frequency to look at. The basic infrared, we look at the wave number start from 4,000 down to about 400. Okay, this is fairly wide range. But as organic chemists, we typically focus on the range that is between 4,000 and 1,600, this range. And this range, we call them diagnostic range, because we can use this to identify the presence or absence of a certain functional group. And so we focus on this range. The from 1,600 down to 400, this range, it is more for the expert. And this we call them fingerprint range. Fingerprint for the machinery or software. We can use software to identify the compound with the fingerprint range. And the diagnostic range is what the normal organic chemists by eyesight, simply by visual, we use to identify compounds in that range. And so, for example, what a difference. And this is an example, ether and alcohol. By the way, the ether we use in this example, they are isomers, have exactly the same number of carbon, hydrogen, and oxygen atoms. And but this is the ether, have no OH bond, OH bond. The oxygen bond with carbons. And so this molecule have no hydrogen bonding, whereas the isomer ethanol has one OH bond, can form hydrogen bonding. And you can see the difference in the spectrum, in the IR spectrum. The one without OH have very significant peak, the absorption, around 3000. This is a typical come from the carbon-hydrogen bond. And there's another one, the carbon-oxygen bond in the around the 1000 area. But with molecules with OH bond, which is capable of form hydrogen bonding, it has a very prominent wave number that is around 3300, fairly strong and wide. The width, because the hydrogen bonding are present. And there's some other CH bond that come from the carbon-hydrogen bond in the molecule. And so also you can see this part have some difference in the spectrum. But typically we don't look at the below 1600, keep in mind. And if you compare another molecule which is similar, both molecules have hydrogen bonding, OH and carboxylic acid. Okay. So use ethanol as an example for the alcohol, has OH bond. Carboxylic acid has carbonyl and OH. And by comparing these two, we can see the fairly big difference. This OH bond causes hydrogen bonding, so around 3300, very strong absorption. And this part is some CH bond. This is CH bond, carbon-hydrogen bond, and there's CO bond here. But if you look at the acetic acid, you have much stronger absorption around the 3200 wavelengths, wave number. And the other very prominent, the above 1600 is where 1700 nanometer have very strong absorption. This is the coming from the carbonyl. You can see the alcohol have no carbonyl, so no absorption around 1700. But with acetic acid, very strong. So this is how the infrared can help us decide the presence or absence of the certain functional group. So between these two, we can both show the OH functional group. And the acetic acid, where the 1700 centimeter inverse, that wave number, it shows the presence of a carbonyl. And so in organic chemistry, it becomes very useful, and especially in the next semester. The frequency or wave number, it depends on the bond, even the same bond, or similar bond. Let's say they both have carbon. And since we're doing organic chemistry, almost all the bonds in the molecule have carbon, almost. And when the carbon bond with some other atoms, what about frequency? The basic physics, the physics tells us the frequency of the vibration, it depends on a constant, and times the, there's a force constant based on the bond strength. So for example, single, double, triple, they have different bond force constant. But given the same type of bonding, the mass, or the reduced mass, consider the momentum. The reduced mass, it depends on what kind of atom in the bond. When you have the same carbon and the other atom getting more and more higher mass, the reduced mass will increase. And that will cause a frequency decrease. So with this equation, we actually don't need to memorize this equation. What matters is when you have a bond, you can see similar. All of them contain carbon and some other atoms. Then the frequency depends on the mass of the other atom. the heavier or higher mass of the other atom, it causes lower frequency in the infrared. So this shows you the these numbers shows you both the force factor, the force constant, and the mass effective frequency. So for example, these three bonds, they are between carbon and nitrogen. And when you have a more multiple bond, triple bond, which have a 1 sigma and 2 pi, it gives you the strongest bond among these three. And the carbon-nitrogen double bond will be next. Carbon-nitrogen single bond will be the weakest. So the difference among these three are basically the force constant difference. The more multiple bond gives you stronger bond, and the frequency, the force constant become larger, you have higher frequency. That's the how does the bond order or the bond strength affect the frequency. The more important it is when you look at the when all the bonds have a same carbon and the other atom, you can see the mass increasing and then frequency decreasing. This is just pure hydrogen with one proton, no neutrons. This bond absorption is around 3,000 wave number. If you replace the hydrogen with the isotope deuterium, which is twice heavy, that causes the mass increase and the frequency will decrease, therefore, fairly significant decrease. And then if you keep increase the mass of the other atom, now become oxygen, even heavier, the frequency even decrease further. To the chlorine, the frequency becomes 700 centimeter. But once the wave number getting to below 1600, we don't look at them because over there tend to be very busy. It's kind of hard to decide what bonds are present or absent. We'll focus on the higher frequency, higher wavelength absorptions. The infrared, even the same kind of bond, same kind of carbon-hydrogen bond, for example, the frequency have a subtle difference. And this, when in the organic chemistry, we identify between the such as hydrocarbons. The hydrocarbons have a wide range of compounds. We can use the subtle difference between these to identify. The reason because as a carbon, hybridization has more S factors. The frequency tend to be higher. So for example, this carbon sp3 hybridization has only 25% S character. And the frequency is 2900 wave number. Once getting the alkene, there's a carbon-carbon double bond. Then the hybridization has a 33% S character, and that will make that higher frequency. Even higher when the S is half of the hybridization. So when this hydrogen bond with the sp hybrid orbitals, the frequency is even higher. So with the waves, those frequency difference, it can help us identify the presence of alkenes or alkynes. And so that's actually how the infrared looks like. The first one is just alkane. The alkane have only sp3 hybridization carbon, and the absorption mainly on the 2900. You can see these are the 3000 is cutoff line. Okay, 3000. The 2900, that's where the alkane CH bond absorption. And now if you look at the alkene have a carbon-carbon double bond. This carbon is sp2 hybridization. And any hydrogen on the double bond, because a higher S character, it shows in the higher frequency absorption. And so the sp2 hybrid carbon bond with hydrogen absorption show up in the 3100, almost 3100, a little bit more than that. And finally, the alkyne. The alkyne is typically the carbon-carbon triple bond. And if this triple bond is in the end of the molecule, then this triple bond can link with one hydrogen. This hydrogen, even though it's very small in number, it has a very significant, very unique wavelength. Is around 33, around 3300, and very sharp. And that's because there's no hydrogen bonding involved. It's very sharp and a very unique frequency. That can show us if this compound is alkyne, by looking at the wavelength, the frequency around 3300 wave number. And so this is the so these are the little practice on what to expect with the given molecular structures. So this is the alkyne. If there's an alkyne and the alkyne has a hydrogen attached to the triple bond of carbon, then you would have 3300 wave number absorbance. So the first one, it is 0.2. Come from a triple bond of carbon, sp hybridization. And this 3100 is double bond of carbon with hydrogen. And the last one, just the sp3 carbon, sp3 hybrid carbon with hydrogen. It's typically just single bond with hydrogen. So by looking at these three compounds, just look at the structure, we can know what kind of carbon hydrogen absorption each molecule should have. Okay, if you look at the first molecule, this is methyl group, and this is also methyl group. And so this carbon must have hydrogen. So for the first one, we would expect to have plenty of the sp3 hybrid carbon with hydrogen bond, which is a majority should have C. The C is 2900 wave number. This structure should have a fairly strong absorption on the 2900. And also we have a carbon hydrogen bound on the carbon-carbon double bond. This is sp2 hybridization. So we should have a absorption on the B, the 3100 wave number. So by looking at the structure, we can predict what kind of frequency, wave number this compound should have. Okay, look at the compound B. The compound B, we have these are CH, and this is carbon have two hydrogens. So these should belong to the sp3 hybrid carbon with hydrogen bonding, which is C. We should have abundant of absorption on the C, 2900 wave number. And do we have a B absorption? B, which means the carbon with double bond can form a bond with hydrogen. We need to have this hydrogen, but we don't have in this structure, so there's no B. And finally, A has to be the sp hybridized carbon with hydrogen. That we don't have. So we don't have these two. But this structure have OH bond. So keep in mind, OH bond oftentimes is easiest to tell. It should be around the 3300 and a very wide peak. So by saying wide, okay, let's say I have two peaks. One is this peak and this peak. This peak, it looks like a steeple, like the church tower at the top, steeple, very steep and very sharp. This is what we call sharp. And this is much broader, looks like a hill, looks like a mountain. This is kind of wide, and this is kind of sharp. So with the second molecule, we should have a very wide absorbance around the 3300. Does not come from the CH bond, it comes from the OH bond. Okay, come from the OH bond. And finally, look at molecule 3. Molecule 3, we have a methyl group here, methyl. So we have a bunch of methyl group. The absorption on the C range, 2900, should be abundant. And do we have a B? Do we have a hydrogen attached with double bond carbon? Anyone? Can anyone tell me? We don't have, right? We don't have a hydrogen attached to the carbon-carbon double bond. This carbon, we link with carbon. So there's no B. And what about A? A need a triple bond carbon with hydrogen. That we don't have either. Even though there's an alkyne, but the alkyne is not linked with the hydrogen. The hydrogen does not bond with a triple bond carbon. We don't have this in the structure. So therefore, we don't have the 3300 wave number absorption. So that's how the, based on the molecule, look at the structure, we can predict what the wavelengths have a strong absorption or wide absorption or not. And that's what we use as a sign to identify organic molecules. Okay, resonance effect. As we can see from that little equation about wave number, the wave number or frequency is proportional, the frequency proportional to the force constant or the bond order over the mass, the reduced mass. It should be reduced mass, but you can see the correlation between the mass and the reduced mass. The higher mass causes you higher reduced mass. It's physics term. The force constant depends on the bond order. And so if bound, because of resonance, it vibrates, it oscillates between single and double or double and triple, then the resonance will affect the frequency. And so, for example, the ketone. The ketone, it have the resonance because the pi electron between the carbon and oxygen in the double bond can be more attracted to the high electron negativity oxygen. So the resonance contributor, it is the a polarized carbon-oxygen single bond. Okay. And so it depends on, this is the, we call it the standard carbon-oxygen double bond, the carbonyl bond. We have such frequency. And compare with this resonance, if we look at some other molecule and structures, if there are more resonance and they cause a more significant carbon-oxygen single bond, then we would expect the force constant. The force constant should be smaller because lower degrees of bond order due to resonance. And then the frequency would decrease, would become lower. More resonance that make the carbon-oxygen have a single bond possibility, then we would expect the wave number or frequency more shifted toward the lower frequency, the 1100 range. So that's what happened if you look at the other structures. This is standard, we just seen that before. And if you look at this molecule, we call it conjugated ketone. Conjugated ketones when the carbonyl link with the carbon-carbon double bond. When you have this kind of structure, there can be a fairly easy resonance. The resonance go because high electron activity oxygen it will cause a molecule have resonance like this, where you can see the carbon-oxygen bond have a strong single bond character. By the way, this resonance, because of resonance, this is in addition to the normal carbonyl resonance. For this molecule, it has these 3 resonance contributors, whereas this one have only 1 more contributor, as we see in the last slide. And so you can see in this conjugated ketone, the resonance, you can see there are 2 contributors have a carbon-oxygen single bond, whereas the ketone have only 1 contributor have a carbon-oxygen single bond. So the conjugated ketone, it shows more carbon-oxygen single bond character, which makes this absorption frequency tend to be in the lower frequency direction. Okay, make sense? More resonance, and if the resonance gives a certain bond, lower bond order effect, then the frequency will decrease. And you can see the frequency decrease is a 40 wave number difference. That's fairly significant. And you can tell with these 2 compounds put side by side, you see the carbonyl absorption have a fairly significant shift to the lower frequency or lower wave number direction. And then the ester. Ester is when you have the carbonyl and carbonyl linked with oxygen. The oxygen, compared with the ketone, oxygen have a higher electron activity. So that makes this bond slightly less like a double bond in terms of resonance. Less like the single bonds, right? That's a single bond. More like a double bond. Therefore, the frequency is higher. The frequency is higher. But anyway, that's not the main point we compare. Oftentimes, the wave numbers, as a matter of fact, we should over time memorize some of the wave numbers. Okay, if you compare these 2, it's more interesting. This ester have no double bond linked with the carbonyl. And the right hand, the ester have a double bond link with the carbonyl. So therefore, there's a resonance. The resonance, it is same as we see in the earlier example. The results is you have carbon, oxygen have more single bond character. This bond have more single bond character. And you can see the wave number is less, 30 less than the unconjugated, just the regular ester. So basically you see the same effect. When you have the resonance, when you have the conjugated double bond, it increases the single bond character for those carbonyl, which lead to the lower frequency for the absorption. So the property like this, it helps organic chemists to identify which is which. And especially when we have 2 compounds, we know there are 2 compounds are these 2. And if you want to tell which is which, you oftentimes use the infrared and tell which is which. And this is much better than just using other physical properties such as the boiling point, solubility, reactivity. Those need a significant amount of chemicals. Whereas use the infrared, just take milligrams, for example. You can just identify these 2 compounds, which is which. Signal strength. The signal strength, the downward peak, the longer it is, means stronger absorption. Lower transmitters, stronger absorption. Stronger absorption corresponds to stronger signal. and this is a relatively weak signal. So the what affects the signal strength? It is complicated. The signal strength, first of all, supposedly the is number bound. The more bound, then it should have a stronger signal. But the challenge is, from the physics point of view, a polar bound vibration or oscillation will cause infrared absorbance. And so the bound polarity or symmetry, it really affected the signal strength. So this shows you the CH bond is between the carbon and oxygen. The bond is not equally shared. Bound electrons not equally shared. So it shows you the carbonyl CO double bond, because a polar bond, it has a stronger absorption than a symmetrical carbon-carbon bond, and that's the polarity. And if a molecule perfectly symmetrical, let's say the 2,3-dimethyl 2-butene, 2,3-dimethyl 2-butene, so that molecule looks like this. This molecule is perfectly symmetrical. And because the carbon-carbon bond is a perfectly symmetrical, it is non-polar molecule altogether, it actually has no absorption around the supposed 1500 to 2000, where the carbon-carbon double bond should show up. Because when you have molecule perfectly symmetrical, non-polar, this oscillation will not cause infrared absorption. So the symmetry, oftentimes, we do not encounter very often, because in organic molecule, most molecules not symmetrical, only very unique. Then we can predict the symmetric molecules would have much fewer absorption because of symmetry. And of course, number of bonds affect infrared strength. The more such a bond will cause a stronger absorption. And the CH bond in particular, the CH bond, because the lower difference between the carbon and hydrogen in the electron activity, the bond is not polar. It's not very polar. So the signal fairly weak compared with the other bonds. But because in organic compound, the number of hydrogen oftentimes is twice as much as carbon, then the carbon's hydrogen bond is very abundant. So in the end, still cause fairly strong signals, just because the number of carbon-hydrogen bonds is fairly large. And actually, in the industry, in real life, we do use this to quantify. And this is the breathalyzer, one of the tests on the DUI, test on the driver DUI. The breathalyzer, in real life, there's quite different kinds. And as I read last night, there's some of the breathalyzer use the infrared absorption from the alcohol. We can use that. And also, some of them use redox reactions between the alcohol and oxygen and measure how much current, which is very small. And that's used the fuel cell. Some of you will learn about the electrochemistry last semester, the fuel cell. The alcohol comes from the breath, becomes the fuel. And with the catalyst, with the other electrode, it produces current by the oxidation of the alcohol. And that current is proportional to the number of alcohol molecules. So that can be very accurate, determine the alcohol level in the breath. But this level, the intoxilizer, it is using the how strong the absorbance come from CH bond. Because from our breath, the exhale from our mouths have lots of nitrogen gas, oxygen gas, water, and the CO2, fairly significant, and the alcohol. The alcohol, if you have the ethanol, you can see among these molecules, nitrogen and oxygen have no infrared because both are non-polar molecule. Water have infrared, that's about very significant, around 33, very wide range, very wide peak. Carbon dioxide is in about 2,000, around 2,000, because carbon oxygen double bond. The ethanol have OH. The OH will overlap with water. So we cannot use OH to quantify the alcohol from the breath. Instead, we use a CH. You can see the CH bond is very unique among all the components in the breath. So we use how strong the signal from CH to quantify how much alcohol level in the breath. Signal shape, very important. These are broad signals. Broad signal in organic chemistry, oftentimes just write down the BR, broad signals. Narrow signal, just N. Strong signals will be STR or ST. Weak signal, just W. So these are the shorthand for those. The OH stretching signals. OH bond is in the alcohol or carboxylic acid. They all have the OH bond. And the OH bond, oftentimes they are so obvious, you can tell this molecule has this bond by looking at about 3,300 wave number. Very broad, because of hydrogen bonding. The hydrogen bonding, it makes the OH bond very broad and strong. If the molecule have OH bond, but because of molecular geometry, the OH bond cannot interact each other and forming hydrogen bond, such as the alcohol molecule in the gas state, very diluted gas state, or a molecule, the OH is not accessible to form hydrogen bonding. So either case, the OH bond cannot form hydrogen bonding, then that'll become more narrow. So not always OH bond can be just broad and then strong. Depends on if there's hydrogen bonding. So this is the, we have example have a very sharp around the 3,700 nanometer. That's the typical for the OH bond. But this molecule, it has a very broad OH bond, and versus a very sharp, weak OH bond. This has come from the OH that is not in the hydrogen bonding, not involved in hydrogen bonding. And the other very broad and strong are the involved in the hydrogen bonding, OH bond. And this molecule, you can also see some other features, such as you have some 2900 that looks like an alcohol, 2900 wave number absorption. So that just tells you some other structures. This molecule does not have very strong around 1700. I'm kind of disappointed because if you have that, that is carbon nickel bound. But that's why we can use the infrared to tell if the functional group is present or absent. Carboxylic acid. The carboxylic acid has this functional group in addition to all the other functional group that in the typical hydrocarbon. So we have one functional group and there's another. So these two we can tell from the infrared. So you can see this, you have very strong absorbance. It's centered around the 3,300. This is about center. This peak, it comes from the OH that is involved in the hydrogen bonding. And the carboxylic acid molecule, even in the gas state, can form hydrogen bonding because the two molecules can form hydrogen bonding to each other. So you have very strong OH bond. And this part comes from CH bond in the below around 3000, very sharp. And there's another one, the 1700. This is very prominent. It is tells you obviously there's a CO double bond carbonyl. So that's and the reason we have very strong, it is because even the carboxylic acid in the gas state, they can form a, we call them dimers. So two molecules form some kind of bonding to each other, either permanent bonding or have a hydrogen bonding. So when the two carboxylic acid interact with each other, the carbonyl form hydrogen bonding with OH in another molecule. And the OH in this molecule form hydrogen bonding with carbonyl in the other. So it will perfectly have a two hydrogen bonding, make it very stable, form like a ring structure, stable. So with that, we learned we should be able to predict the infrared, where what wave number, what is shape for the absorptions. Like we go over the CH bond, OH bond, they are above or around 3000 wave number. And the other bond is the carbonyl, CO double bond, around 1700. And so that's basically we learned just in this class. The CC double bond also has around 16 or below 1600 wave number absorption. And so by looking at this molecule, with this molecule, it's important to show all the hydrogens. Show all the hydrogens. This is a methyl group. And here we have one more hydrogen. So keep in mind, in the infrared, a hydrogen oftentimes it is very strongly tells us information about the structure. Because hydrogen, it is a lower atomic mass. So the frequency oftentimes in the higher frequency range, at least 2000. And that can tell us what kind of structure the molecule have. And then we have carbonyl and OH. So what is unique in this molecules? We have this kind of structure, and we have this. And we have the carbon-carbon double bond. The carbon-carbon double bond, we may or may not be able to tell. There's many other bonds in this molecule, but as far as we learned, we focus on the diagnostic, which means wave number between 3000 down to about 1600 wave number. We want to focus on this range. And the others, such as carbon-oxygen bond or carbon-carbon, single bond or double bond, these are frequency, and especially the carbon-carbon single bond, is an even lower frequency. We don't look at them. And so with that, we can just determine what wave number there could be the absorbance. They start from the high wave number around 4000. We first look at this. This should give us the around 33, and very wide, because two of such carboxylic acid molecules can form hydrogen bonding. So we should expect wide and strong around this wave number absorption. And then the still around 3000, we look at the other. CH, this bond, because carbon's sp2 hybridization, the wave number is around 3000, 3100. But since there's only one bond, it should be fairly weak and sharp. So is a weak bond. Weak WK for weak. There should be only one tiny peak, little spur. And then you look at the still around 3,000. These are abundant. You have two methyl group. The methyl group is a carbon-hydrogen single bond, and the carbon sp3 hybridization. So we should expect fairly strong because it's 6 carbon-hydrogen bond. Very strong, but this should be still weaker than the OH bond. And this should be fairly significant. So we're done with around 3,000 wave number. We move down to below 3,000. Below 3,000, the carbonyl. Carbonyl, it should be around the 1700. But notice this carbonyl have a carbon-carbon double bond linked together. This we call them conjugated ketone, actually conjugated carboxylic acid. And the double bond will bring down the frequency. So I would expect around 1700, maybe slightly less than 1700. Because the double bond linked with the carbon-carbon double bond linked with the carbonyl. You should have very strong 1700. But the wave number is less than the typical 1720. And then finally the carbon-carbon double bond, it should have about 1600 wave number, but oftentimes that's the carbon-carbon double bond oftentimes difficult to identify. They're oftentimes mixed with other absorptions. So as far as the diagnostic, we focus on the one we see in those numbers. And the carbon-carbon double bond is we typically do not look at that. So that's how the give you organic molecule based on the absorption frequency that in our knowledge, we can predict what kind of frequency there should be absorption. And by comparing, look at the real infrared spectra, we can tell if the molecule given, it is this molecule or not. And then next into some other molecules, amine. Okay, amine have a NH bond. Not all the amine have NH bond. Only the amine such as amino group, or the hydrogen have 2 carbons. This is also amine. When you have this kind of structures, the NH bond being a fairly polar bond, that should have fairly strong absorption and high frequency as well. Of course, tertiary amines, which means the nitrogen bound with 3 carbons, have no NH bond, so there's no absorption. And the NH bond, because they can form hydrogen bonding, they're oftentimes very broad. But NH bond is less polar than OH, so it's weaker. So it's a broad but weaker bond. The NH bond in our class, we do not use that much. We may not put into our test. Next semester, when you study the amine and chemical reactions, amine, how to synthesize amine, you will see the amine more in the next semester. So here's some examples. The first one's nitrogen have 2 hydrogens. And this molecule, by the way, this molecule mostly have a CH bond, and the carbon's sp3 hybridization. So you have fairly strong 2900 wave number absorption come from the CH bond. The NH2, it shows you a 2 peaks. These are above the 3300. So definitely this is not a CH, the alkyne CH bond. It comes from a polar NH bond. And this is the amine. We call them primary amine because the carbon linked with the amino group have only one more carbon, only one carbon. That's why you call it primary. When you have a secondary amine, which means nitrogen linked with 2 carbon and 1 hydrogen, secondary. And there's only 1 H bond. And you can see there's only 1 peak. Only 1 peak. The frequency is above 3300 and fairly wide. It's a big difference compared with the alkyne CH bond. Alkyne CH bond is very small and sharp because it does not form hydrogen bonding. Okay, so the signals oftentimes tells the difference in the structure. And by the way, the amine in the high wave number absorption, you can see they are strong, but not as strong as OH. Okay, what OH looks like if I draw it on this chart. Okay, I'll draw the OH bond. If I draw the OH bond, that looks like this. If this molecule have OH, it looks like much stronger absorption, and much stronger, much wider. It looks like a mountain. These are just like 2 teeth, like a fang of a snake. The real OH bond is much deeper, stronger absorption, wider absorption. So that's difference among different kind of bonding. And the shape for the NH, the amino group, has a very signature, fairly strong. It's like a moderate, strong, and twin peaks. Not quite twin, but they're together, 2 peaks. So these are the, I can tell you there's amino group in the molecule. Sometimes we, in the organic chemistry, to identify what kind of amine in the structure, we use the around 3400 if there's a 2 NH2 absorption peaks or not. Because the stretching, there are 2 kinds of stretching. One is the symmetrical. The other one is asymmetrical stretching. And these 2 stretching cause the difference in the frequency. The vibrations and a single molecule. So the all these molecules vibration, they all shows us signals. Even though the pattern is different, their frequency can be similar, and oftentimes as a signal they are close together, close to each other. Solvent, nowadays many infrared measurement is done by just pure sample without any either the put on the salt plate like we mentioned before, or just the powder themselves put on the infrared and directly measure, like in our lab. In the older days, organic compounds, they are not soluble. We have to put in solvent. The solvent molecules can have interaction with solute molecules, with sample molecules. So there will be effect on the appearance, absorption, strength of the infrared. And nowadays we don't really use that, but we should be aware of what kind of environment, what kind of solvent we use, and that can cause difference in infrared in the appearance, the strength, wave number, and appearance. So these 2 the example we have. This is acetic acid that dissolved in carbon tetrachloride solution. In the solution. The second example is the acetic acid in the gas state. You can see the big difference, and especially the OH bond. The OH bond in the solution becomes much stronger and wider absorption, stronger, wider. And the OH, because of hydrogen bonding in between molecules become more frequent, they become much stronger. The carbon-hydrogen bond, it should be slightly less than the 3000. That has pretty much been buried by the wide OH bond. You can barely see them. And notice also this is CO carbonyl bond. The wave number looks like around 1700, okay, by counting the grids. Okay, in the gas state molecules, has more individual molecules. There's some molecules can form dimer to form give you hydrogen bonding, but most of the acidic acid molecule as individual molecule, there will be no hydrogen bonding with the individual single the acidic acid molecule. So the OH absorption become much sharper, very sharp, and not that strong. Okay, it's strong, but not that strong. And you can still see the 3CH group has a very almost negligible peak around the 2900. So this is mainly OH, hydrogen bonding free from hydrogen bonding, very sharp absorption. And then the OH bond, the carbonyl bond in the gas state also have a fairly significant shift, now become 1800 wave number. So there are changes in the structure. And actually interesting to see this carbon oxygen, the frequency actually become increased. This can be at least partially explained because when they form hydrogen bonding, when there is hydrogen bonding, the oxygen will be attracted to the hydrogen. So that's if they have hydrogen bonding. And that means the electrons will kind of move away from oxygen and towards the hydrogen. So that's sort of makes this double bond character weaker because the positive hydrogen attract. So anyway, you can see the difference. Even the same molecules, when you have a different solvent, so there's some changes in the absorption pattern and even the frequency. For some bonds, there's a frequency change. The key signals for functional group they start from the 34,000 wave number down to about 1600 wave number. And later I'll give you a chart about those frequencies and the wave pattern, signal pattern, absorption patterns. So the diagnostic is our main focus. Diagnostic mainly the first double bond, and especially carbonyl bond, just oftentimes because more polar, much stronger. And you look around 2000. 2000 is where you look for the triple bond, carbon-nitrogen triple bond. Even though the bond is heavy atoms, both are carbon-carbon, carbon-nitrogen, the triple bond gives you stronger bonding, so you have frequencies high enough. You can see from that range. And typically they are very small and sharp because this kind of bond in the molecule oftentimes is not a large number. And then the CH bond, the three different hybridizations, sp3, sp2, sp hybridization, carbon with hydrogen have a different frequencies. That's what I can use. And OH bond oftentimes very broad and strong. NH also very high frequency, but much less. So these are the frequency patterns we can use to look at the structure. And so these are the so this is basically based on the around 3000 the single bond, what a single bond with hydrogen they have. The OH bond oftentimes very steep, very steep. That's the OH bond. NH bond is a much still high frequency, but NH bond is much smaller. It's this kind of shape. CH bond is very tiny, only the bump around 3300 wave number. And then 31 is also very small because the double bond, the number of double bond in the molecule is oftentimes limited. You have very small. And then below 3000, that's typical for the sp3 hybridization, carbon and the hydrogen bond. That's where it shows up. And so that's, okay, let's see. Unlike NMR, which we will learn next semester, infrared is not very precise about the molecular formulas. For example, how many hydrogen, how many carbon, infrared cannot tell. But infrared, oftentimes, it can be used for tell the difference, the absence or presence of a certain functional group. And especially when you have two compounds, we kind of know what a function group in each molecules. Then we just compare the infrared and find out if the molecules are present. Or the one compound is the one and who's who, basically. Infrared is more a tell about who is who. When you have a pair or couple compounds, you know the formulas, but don't know which one has what formula, they use infrared, very helpful. And so, for example, this is the situation we have. This molecule is a alcohol, and alcohol is a fairly reactive molecule. It can go through chemical reaction, becomes many other chemicals. One of the reactions is the oxidation reaction, produce a ketone. So let's say in the industry or pharmaceutical organic synthesis, we make molecules from the raw material, alcohol, and the final goal is to get a ketone. So how much of the, in the reaction, and in a typical reaction, organic chemical reaction, oftentimes is more time consuming, and oftentimes they are byproducts, kind of messy. So we have a slow reaction, and you want to know if the reaction is complete, then use the difference in the functional group and do an IR, do infrared, and we can know if the reactant is still present or how much reactant is still present. So for example, between the alcohol and carbonyl, as the reaction progresses, we should have less alcohol in the reactant, in the reaction mixture, and there'll be more ketone formed. So if you want to know, is the alcohol completely reacted or no? Just do an infrared. Take example. Take example of the reaction mixture and measure and observe around the 3300 wave number absorption. If you still see fairly significant and strong, very broad, that means you have still quite a bit of reactant not reacting. So keep going, give more time. But if you see there's almost negligible, the 3300 wave number absorption, that means OH is fairly complete. And keep in mind, in the real organic chemistry, we almost never wait until the reactant 100% react. It's just because reaction takes long, and also getting slower as the reactant is being consumed. So it's about degrees of how much reactant being converted. And all right, this is kind of an application. I go fairly quick on this. In the future, when we get into the real chemicals in the following chapters, we might be able to see how the infrared is used for the chemical reactions. So let's say the first step, we have This is the alkene and reaction with HBr. HBr reaction, first step, it will add the bromine to this molecule, and H add to this. Once added, there's no more double bond. You got a single bond. That's the first step. And the second step, we use a strong base to eliminate the bromide. And after eliminating bromide, they form a new double bond, which is here. So that's what you see. Finally, we give you a different alkene by the two-step reaction. So how can I use IR to differentiate these two? This first reactant have a CH on the double bond. First reactant have CH in the double bond. And final product, there's no hydrogen on the double bond. And the CH double bond have a very unique, fairly weak, sharp, but unique, is around 3100 wave number. So by observing, monitoring the how much signal on the 3100, that can tell us how much of the reactant being converted into product. So that's where the first step you can use a CH bond. Because in the product, there's no CH bond on the double bond. Okay, what about final step? You can see the with this alkene, it reacts with ozone, the O3, and with followed by a reducing agent. The final product gives us two ketones. So how do you know the products being formed? You can see the product have a CO double bond, a carbonyl, where the reactant is a CC double bond. CO double bond has a very unique, around 1700 wave number absorption, very strong. So by monitoring the 1700, the signal increase, that can tell us how much the product is being formed. Is the reaction complete or no? We can check the 1700 wave number.